let's see what should happen when we pop things from the stack. So let's say that we have two threads that want to pop the first item, and it will set a local variable that is a copy of the current value of top to this one, and another thread will do the same. Okay, and then it will use, or they will use this atomic, well, I abbreviated again, atomic compare exchange with the value of the stack with their local variable, and if the top and this local variable point to the same thing, it should set the top to the new value, I mean its new value, which is the next of this one. Okay, of course, before that it should check if top is non-null, otherwise it will be a segmentation fault. Okay, so what can go wrong here? Or what, well, we can actually start with seeing what can work. So both threads do this, and one of them will succeed, say T1 succeeds, and it moves top to the next item. Okay. So now it's the other thread's turn, and it will compare its value here with the top, and they are not the same, so it will not update the top to A2. I mean, this 7 has already been popped. So, but what happens is that instead it will copy the current value of top into A. So this one will move here. Okay, that looks all nice, and then thread 2 can do another attempt, and eventually it will succeed. Okay, let's look at the source code. So here is the pop. Well, that we can skip. Okay, so it starts copying the top of the stack, and if it's not null, then it will try to do what I just showed. But if it was null, in this stack it returns a 0, and if not, it takes the key and returns it. Okay, so here it says if free, and if free is controlled by this macro. So at the moment it's 0, and the code for free is, this call will not be performed. So let's see what happens when we run this. Okay, it appears to work nicely. Okay, so it does 10 tests with 80 threads and 100 things to push and pop. Well, actually more, because it's multiplied. This number of items is what each thread should pop. So the thread that pushes, there's only one. It will push more, obviously. Okay, we can do more tests. If this code should sit in an airplane or nuclear reactor or break in a car, it should be tested not only a few seconds but a long time. Okay, so let's do this by enabling freeing each node after it has been removed from the stack. What do you think will happen? It will not be pretty. So what we do now is to free this. What can go wrong? Double, free, or corruption. Okay, another time. Okay, nothing happened. I mean, it's just well, this is not what we want in neither our programs or in somebody's airplane. Okay, so what can have happened? There are different things that can go wrong. When thread 1 okay, so we had well, actually we can rewind this to this. When thread 1 so both thread 1 and thread 2 come to the pop function. Okay, so they both load the top of the stack, so they are both here, and then we can say that thread 2 is suffering some cache miss or something else, so only thread 1 continues. Okay, and what it does is to well, it gets this node and it actually frees this node. Okay, what happens at the free? Well, we don't know, but well, we know that it is returned to the heap manager, but after that we have no idea what the data will be used for. But what we know is that this node is no longer existing. Perhaps that memory was overwritten, and so this memory is now overwritten. Oops. Well, let's do like this. Okay, maybe I should have this color instead, but okay, so and now it is something terrible will happen, namely that somebody writes a string here. Okay, unlucky you. Unlucky. Okay, and thread 2, what will it do? Now thread 2 wakes up, and okay, so it takes the address of the top, that's fine. It takes the address of A. Is that okay? Yes, it is. The address of A, that's the local variable here. That's fine. I mean, we can take the address of a local variable even if it doesn't point anywhere. Well, it does point somewhere, but that data has been freed, so it's an invalid pointer. But here comes the troubles. Oh, I forgot that one. When we read the next field from this invalid pointer, I mean from where it was supposed to point, it will read some bits by interpreting these characters as address bits, and then it will, well, it will not find 7 there probably. It will just segfault. Okay, so let's see if that was the thing that happened. Well, possibly double free or corruption. There can be different things that happen. Nothing happened there, but okay, segfault was one happy printout here. So that's one problem that that we just saw. Okay. What else can go wrong? Let's rewind this again. Okay, that one should still be there. Okay, and we add this. Okay, so now we come to the ABA problem. Okay, so let's say that T3 is also interested in this. Okay, so it sets it here. Okay, now let's say that a thread 1 succeeds in popping this. Okay, so the top of the stack is changed to 5, and this one is well, it's freed. Okay, so we can say freed, but we can assume that thread 2 and 3 were able to read the next pointer, just to be well, I don't know if it's pleasant or not, but just for the example. So they have read this, and 7 that's freed, so it doesn't exist. Okay, and then thread 2 is we can say that thread 2 is it returned and updated its local variable to node with 5, and it rereads A, and it does this again. Okay, and now it will evaluate this parameter again, so it will not read that one. Instead, A next is this one. Okay, so say now that it succeeds in popping this node. Okay, so now that one is also gone. Okay, and the top of the stack is pointing to this one. Okay. T3 is still sleeping, and now let's say that thread, well, it doesn't matter which thread it is, it's not thread, we can say thread 4, it wants to push. Okay, and it succeeds, so it well, it will succeed after updating the top, but anyway, it allocates memory, and here is I mean the memory for this node, it's in the heap, and when this node, this thread says malloc or calloc a node, it can take this one, so it does. So now that one is reused, and it writes 13 there, for instance, and then it sets the next pointer to to the top of the stack, and it succeeds in updating the stack pointer, so now that one is moved over there. Okay, and now it's time for thread 3 to wake up again. What is going to happen? Well, recall where it left off, and this is really important. It read the parameters, and this I mean, it's the address of this variable, so it will be fine. It will always be valid when we come to this function. The address of the local variable A3, that local variable pointed to this node. Okay, that node was freed, and this thread allocated the same memory, so actually A3 now in reality points to this node. I mean, node with number 7 was located at the same address as the node with number 13. Okay, why should that be a problem? Well, we will see soon. Okay, and the third parameter of this call, it will have the a next field, and I mean, the worst case is that we evaluated this before going to sleep. So this a next was the value just before falling asleep. Okay, and what was it? It was this pointer. So this is a next. I mean, it points to this node, which doesn't exist. It is there, and overwritten with, well, anyway, anything. Okay, so now we come to atomic compare exchange, and what does it do? It compares if top and the second parameter point to the I mean, not the same address, because a is a local variable and top is something else. But if the value are the same, bit by bit, or byte by byte, or 64-bit by 64-bit, or whatever size they have, and they have the same value. I mean, these are equal. Top points to 13, and the local variable of thread 3, well, it was supposed to point to a node with value 7, but the same address is reused for the node with value 13, which is the top of the stack. Okay, fine, says atomic compare exchange. Let's set the top of the stack to the third parameter. Okay, now you may think that a next would be this next, but it's not. It is, I mean, it could have been if it fell, if thread 3 fell asleep before evaluating the argument, and then when it wakes up again, when I say fall asleep and wake up, it's not of course due to a lock, it's just that it's preempted or got the cache miss, so it just stopped executing. Any thread can stop executing anytime, unless special precautions have been taken, special care, which sometimes is done for safety critical embedded systems, where just as an example, any unpredictable thing is excluded. It could be. I mean, if a cache miss would result in a disaster, then don't use a cache. But okay, we don't have that here, and I'm not at all saying that all safety critical systems avoid caches. That's not the case, but what I'm saying is that a thread can be put to sleep, so to speak, at any clock cycle due to something, such as being preempted by the operating system so that another thread should run, completely different thread. Okay, so if thread 3 was preempted or put to sleep before evaluating this, and now it wakes up, then it would have it will evaluate this and get the correct a next field value. So it will just I mean, it doesn't know that it's a variable points to another node. It can't see it, and this node's next is valid, so it will use it, and that would be fine. But if it was put to sleep just after evaluating the argument. What does it mean, evaluating an argument? Well, in this case, it just means reading this next pointer from memory and putting it in a suitable place so that this function will find it as the third argument. Okay, so if we now assume that this one was evaluated before T3 was put to sleep, it will still have the same value in that argument as it had before going to sleep. So it will be pointing to, well, where will it be pointing? It will be pointing to this node, which is in the heap, waiting to be reallocated. It's invalid anyway. But atomic compare exchange, they will compare this and they are the same, so it will set the top of the stack to this node. So now it's very convenient because it's very nearby, so it's just to say top is there. Okay, and what happens to the next node that will try to get something from the stack? It will use freed memory. Okay, let's see again how this dramatic thread termination can look like. Well, it can look in different ways, but it's not fun the least. Well, it can be fun, but not. It can hurt as well if it's in a safety critical system or in some other important program, such as pre-flow in the competition. Okay. So what is this that we just saw? It is an example of the ABA problem. That this value, it was A3. It was first equal to this valid node, and then that valid node was removed, and it got a new value, and then it was reused to. It was reused with a new node. So first it was A, and then it was B, and then it was A. The pointer was first to this valid, and then it became invalid, and then it became valid again, and thread 3 cannot see the difference, so it assumes that this is okay. Okay, so this is a really problematic thing. Okay, if you use Java, you can be happy now, at least for a moment. It will not occur in Java or other languages with garbage collection, because as long as some thread is having a pointer to the node, that it cannot be recycled. It cannot be garbage collected as long as thread 3 has a reference to this node. Okay, so that's good. But creating and freeing, garbage collecting nodes can take more time than is suitable. So often one uses some kind of pool of objects that can be reused. So instead of doing a new to get an object, one can see if there is one already created that is not being used. This is called, the normal thing of this thing is, the normal name of this thing is to have a so-called free list. Okay, so, or a pool of objects that are not being just deallocated and allocated every time we need one. It's the same idea as having a thread pool when in OpenMP, for instance, that we do not recreate all the threads when we enter a new parallel for loop. We can just reuse the already existing threads. So that is quite common also in Java. Well, how frequent it is, I don't know, but it clearly is an optimization. And in that case, if we do it, then this problem must be somehow addressed. And in the next video, I will show how we can do that.